This lesson is on simplifying radical expressions. Totally radical. Recall that a radical is actually a square root. Let's consider the root of 32. One way of writing root 32 would be to approximate it on a calculator, and you get a nice long decimal which you can round off to 5.657 when it's rounded. However, this decimal goes on, and so it's difficult to know where to cut it off depending on what use you have. So say you're doing a science experiment and somebody wants it to 8 decimal places. Well, that's lost if you give them this answer. However, if you keep it as a root which they can find however many places they would like to use, then it's a bit more exact. Now, so leaving it as root 32 would be better in that case, because then you're giving someone else the choice to round to whatever they want to. However, when we have more roots together in some sort of equation, sometimes it's nice to simplify, and we're going to look at that in the next lesson. However, in order to get there, we need to learn how to simplify each root separately. So consider 32. 32 is actually made up of 2 times 16. Now, can we consider taking the root of 2 and the root of 16 and multiplying them? So the question is, can we split the root over a multiplication statement? Well, let's see. Root 32 is approximately 5.657. Root 2 is approximately 1.414. And root 16 is exactly 4. Notice that when you have the root of a perfect square, it gives you a nice integer, an exact number that doesn't need to be rounded. If it's not a perfect square, it's very likely that you get a long decimal that needs rounding, and it's an irrational number. So these types of numbers that have long roots are often left as roots so that someone else can decide how much they want to cut that number off, to what accuracy they want to consider that number. But let's see if this is actually the same thing. Can we say that the root splits over these two numbers? Well, in that case, we could check 1.414 times 4, and look at that. That gives us 5.656. There's a little tiny bit of a discrepancy there, and that comes from rounding. So we often in mathematics want to eliminate as much rounding as possible and keep it to the most exact version that you could have. So we could actually write root 32 as 4 times the root of 2. And often it's just written 4 root 2. Now this is probably the simplest way of writing it to keep it exact and to be able to combine this number with other similar numbers. In the next lesson, you'll see that. So this is the simplest form of a radical, and that's found when there are no perfect square factors in your root. Also, in this page here, we have noticed that you can split a root amongst multiplication. So basically, if under your root you can find some factor that is a perfect square, you can distribute, or you can separate it into factors and then pull out any perfect square factors up front as exact numbers. Let's consider root 4 over 9. In considering this, we can figure out, can this root be split over division? Well, let's check it out. If it could be, then you would get the root of 4, which is 2, and the root of 9, which is 3. 2/3 is approximately 0.6 repeated. Now let's see what we get when we type this into our calculator. Root of 4/9 is also 0.6 repeated. So therefore, we can split a root over division. But what about addition or subtraction? Well, let's try it. What if we could? What if root of 4 plus 9, could it be a root of 4 plus root of 9? Well, that would mean that that would equal 2 plus 3, which is 5. However, root of 4 plus 9 could also be seen as root of 13. And what's root 13? Well, it's definitely not a nice number, and it's definitely not 5. Root of 13 is 3.6, and so on, approximately. So this is not true. Definitely not true. So if you see some sort of addition or subtraction with any type of root, a cube root, a fourth root, a regular root, you can't say that it splits amongst the terms. So, very important point is that a lot of people, when they see the root of a squared plus b squared, they want to say that that's equal to a plus b. If you had the root of a squared times b squared, then yes, that would be ab, because ab times ab gives us a squared b squared back. However, a plus b times a plus b does not give us a squared plus b squared back. So it's very important to note that you cannot split the root over an addition. Let's move on to simplifying radicals. You saw a little bit of a snip of that in the first slide. Let's continue. So here again, I have the criteria for a simplified root. So simplified square root has no perfect square factors in the radicand, and we saw that with 32. 32 had a perfect square factor of 16 in our previous slide, and so we could basically evaluate the 16 but not the 2. A cube root, a simplified cube root, will have no perfect cube factors, similarly, and so on. A fourth root will have no perfect fourth exponents within it. So let's look at the square root of 300x squared. Because sometimes it's difficult to locate, does this have a perfect square? So I suggest to break down the number. Let's factor 300 and see what it's made up of. And then we can look at creating perfect squares out of those factors. So 300 can be seen as 3 times 100. Okay, so you could notice that 100 is a perfect square because it's 10 times 10. However, let's say you didn't notice that. You could keep factoring and you'd see that, well, 10, yeah, sure, it's 10 times 10. Or you could have said 4 times 25. Let's say that, 4 times 25. 4 is a perfect square and 25 is a perfect square. But say you didn't notice that, you could keep factoring. and you'd notice that 300 is the same as 3 times 2 times 2 times 5 times 5. Okay, so let's just rewrite what we have underneath our root. Instead of 300, we could have had 3 times 2 times 2 times 5 times 5. And we also had x squared, which is x times x. So 3 does not have a pair, so it cannot be made into a perfect square of 9. But 2 has a pair, so notice that if this was written as a 4, then out of the root it could become a 2. The square root of 4 is 2. The square root of 25 is 5. The square root of x squared is x. So you can see that we have 2 times 5 times x that have come out of the root, which becomes 10x, and inside of the root we just have our 3 left. So what we've done is that we've evaluated anything that can be taken out as a perfect square, but left anything that can't. It's really the root 3 that makes the root 300 a nice big decimal. Right? So root 300, you could evaluate that and see what that is. That gives you a decimal, 17.3205 and so on. But you can see root 300 as 3 times 100, which is root 3 times root 100, and root 100 is actually 10. So you could write this as 10 times root 3, and this would be the more exact way of writing root 300, and it would be a simplified radical form. So let's continue and simplify some more radicals. So my suggestion is, especially if you're not familiar with finding perfect squares and factoring, and you don't quite have all those numbers clear in your head and easy to access in there, you can always just break down the whole number exactly. So 28 is 2 times 14. I often use 2 if it's an even number because it's easy to split in half. This one works as well, 2 times 7. So we can see that this is negative 3 times, there's always a little times there, root of 2 times 2 times 7. You'll notice that the two 2's actually make a 4 when multiplied, which when rooted become a 2 again. So we have one factor coming out that is a 2, which can multiply to the outside number here, which was a 3, giving us negative 6. And under the root we still have a 7 that did not have a pair and could not escape the root. So this would be the simplest form of this radical without turning it into a decimal. Let's continue on. This one has a number, so it's similar to this approach, but let's just talk about what happens to the variables and their exponents. So sometimes, in the previous slide, you notice that when you have x squared, it ends up being an x out front. So you could either think of it as, well, I had a pair of x's. The square root of a pair of x's multiplied together is x. But also you could see that because a root is actually asking how many pairs of that thing do you have, well, when you think of how many pairs do you have here, well, you have 2 things, so we have 1 pair. So really you took the 2 and divided it by 2 to make 1. So how would that work here? Let's just consider the a to the 5. If I wrote it out on the side here, a to the 5 would be a times a times a times a. If I was rooting this, I'd notice that every pair of a's gave me an a out because the square root of a squared and square root of a squared again. but there would be one a left. So I could have rewritten root of a to the 5 as the root of a to the 4, an even power, times a. So justify that in your mind, that yes, you can write the 5 as a 4 and a 1. Now, every even root will actually become halved, because how many pairs are in 4? Well, there's 2 pairs. So 2 a's came out. And then we have 1 a left inside. So that's how you can deal with higher powers. So another example would be, say you had the square root of x to the 21. Well, maybe you don't want to write out 21 x's and see how many pairs are in there. You can imagine it in your mind. But you can also write this as x to the 20 times x to the 1, which then gives you the idea that, hey, the square root of x to the 20 is really saying how many pairs can I make in 20? There's 10 pairs. So you're actually only taking half of the exponent when you square a root. You'll notice you'd be dividing it by 3 if it was a cube root. So an x to the 10 comes out, but an x is left inside. So that's a little bit on why things happen to the variables. So let's continue on. So here, there's a negative out front, and this negative just hangs out, just like this one did. Let's see if we can rewrite 48 into smaller factors. So 2 times 24, 24 is 2 times 12, 12 is 2 times 6, 6 is 2 times 3. So that's negative, and then we can write that all out. 2 times 2 times 2 times 2 times 3 times a to the 4 times a, because we want an even power, and then you can always write out an extra one if you have an odd power, and b is also there, and b is another single. So we've got 3 as a single, a as a single, and b as a single. So those will be the ones that have to stay under the root in order to make it in simplest form. The pairs, root of 4 is 2, root of 4 is 2, and then the square root of a to the 4 will be a squared. You can also think, well, if I squared a squared, I'd get a to the 4 back. So we have a negative up front, and then a 2 times 2, which is 4a squared, is all coming out, and we've got 3ab left inside. So this is one way of simplifying roots. Please note that if you are good with seeing perfect squares within numbers, you can go ahead and do that right away. So say you had to take the root of 48, and you knew that 48 is 3 times 16, then you could go ahead and say, well, that's the square root of 3 times the root of 16, and that's the same as 4 root 3. Further, we've got fractions. 2 criteria for simplifying fractions is that we don't ever want to leave any fractions within a radical, and we also don't want any radicals in the denominator of a fraction. Very important, you never want to leave the root in the bottom. So, as before, it's best to simplify inside first, if at all possible, because then your numbers are smaller and they're easier to break down. So, are there any common factors between 108 and 25? No, there are not, so we need to keep that. Now, m cubed and m. Well, m to the 3 over m to the 1 leaves us with m to the 2 in the numerator. n to the 5 over n to the 7 leaves us with n to the 2 in the denominator. The root is still there, however, remember the root can split over the numerator and denominator because it's division. Now let's continue on. We can rewrite 108 into its factored form. If you don't know how to split it up, you can notice that it's an even number, so we can divide 108 by 2, and we get 2 times 54. 54 is 2 times 27. 27 is 3 times 9, and 9 is 3 times 3. So if we write that all out, we get 2 times 2 times 3 times 3 times 3, m squared over 25 is 5 times 5, n squared. Now notice, we've got 2 2's, which would be root 4, which is a 2. 2 3's, which is root 9, which is a 3. 1 3 is left. M squared becomes m because m times m is m squared. And here we've got 5 and an n coming out. So that gives us 2 times 3 times m, which is 6m, and a 3 is left in the root. Don't forget about it. And you've got a 5n and nothing left in a root. You notice there are no common factors. There is no fraction under the root, and there is no root in the denominator. So it is simplified completely. Try the next one. Can we simplify anything in here? In this case, we can't. So let's break it down. In the numerator, we've got 16, which is 4 times 4. Now, if you right away see that it is a perfect square, you can just either write it like this or write it already out front. You don't have to go completely if you see that it's making pairs already with bigger numbers than primes. X cubed we want to write as x squared and times x, because we know x squared will root out to an x. Root 16 will be a 4, but there will be one x left under the root. So on top we'll have 4x root x. Continue. In the bottom we have the root of 81, which is 9 times 9, which in this case I can just keep like that. That'll give me 1 9. And y to the 4, half of 4 is 2, so y squared. Y squared times y squared gives us y to the 4. Check. So that gives us 9y squared in the denominator and nothing left in its root. Therefore, we're good. We have no root in the denominator and no fraction under the root. Again, there's our simplified form. Let's move on to simplifying cube roots. Now, recall, a cube root is basically asking what times what times what, meaning what cubed gives me that. So now we're actually looking for triples, because if you have, say, 2 times 2 times 2, the cube root of that is 2, because 2 has been cubed to get 8. So let's take a similar approach. 54 can be written as, let's break that down, divided by 2, 2 times 27. 27 is 3 times 9, and 9 is 3 times 3. So we can write this as cube root of negative 2 times 3 times 3 times 3 times. Now notice that x to the 4 would be 4 x's. Instead of looking for pairs now, we're looking for triplets. So we're actually trying to get multiples of 3 out of this. So we could write this as x to the 3 times x. And we could write y to the 6 as y to the 6, because we can divide 6 by 3 easily. we will have two triplets within y. We'll have one triplet within the x plus one left over. Notice that I have not said anything about this negative yet, because remember that a cube root of a negative number, negative x cubed for example, is a negative, because negative x cubed will give us negative x cubed. So when you see a negative under a cube root, it's fine. It just hangs out as a negative up front. When you see a square root of a negative, you know it does not exist. So here we have a 2 that does not have anything else to combine with. We have a triplet of 3's, which will leave us cube root of 27, which is just 3. We have a triplet of x's, which will leave us with an x. One x is left by itself, and we have a triplet of, actually two triplets of y's, because two triplets make 6. So really you're dividing the exponent by 3. So that leaves us with y to the 2, because y squared cubed gives us y to the 6. There's many ways of understanding this. If you really want, you can write it all out and look for triplets. Either way, you're left with negative 3xy squared up front, and under the cube root, remember it still stays as a cube root, you're left with a 2 and an x. And that is the simplest form there. Let's continue. Here we've got a fraction we should simplify first before we do anything. 24 and 125 do not have any common factors, so we need to leave those as is. However, m and m to the 7 can simplify to be nothing over, or 1 over m to the 6, which then you have n to the 6 and m to the 6. We're cube rooting a negative, so that leaves a negative up front. And we can split the root over the top and the bottom. Cube root. We can write 24 as 2 times 12, 2 times 6, 2 times 3, as 2 times 2 times 2 times 3, and n to the 6. And in the bottom, we can write 125 as 5 times 25, which is 5 times 5, which is a triplet of 5's, times m to the 6. Notice the sixth powers are divisible by 3, so we're good. We can find triplets within them. So we've got negative, one triplet of 2's comes out, and two triplets of n's come out, one triplet of 5's come out, and two triplets of m's come out. So that leaves us with negative 2n squared cube root of 3 over 5m squared. Nothing simplifies there, and we have no radicals in the denominator and no fractions in the radical. So we're good. Eventually you will see what to do when there is a radical left in the denominator, but that will be found in a further lesson.